our webinar today. Today we are going to be discussing line leakage testing for the 60601-1 3rd edition standard, which covers electronic medical devices. So the scope of this webinar is somewhat more limited than what we had done in the past, where we discussed the full scope of some electrical safety testing per the standard, but there's so much involved with just the line leakage testing itself that we thought that it would warrant its own presentation. So hopefully you gleaned some useful information from this presentation, but before we get started, a couple things. You're going to notice on the webinar screen you have a few utilities at your disposal. So if you look at the right-hand side, you have a chat utility as well as a Q&A utility. And if you're having problems with the audio or the visuals of the WebEx itself, maybe you can't hear me very well or you can't see the slides changing, please use the chat utility and let Jim know so that he can help you out. If you have questions related to the material itself, please use the Q&A utility. We have our applications engineer, Syed Abidi, on as well, and he will be able to assist you with those technical questions. Any questions we may not get to during the webinar, I will save some time at the end for discussion. Sometimes the questions can get a little too in-depth for the purpose of talking about it in this allotted time frame. So if that is the case, you can always feel free to email us directly, info@asresearch.com, and we will have that email up at the end of the presentation as well. This webinar is being recorded and will be available on our website on the webinar archives page in just a few days. If you want a copy of the slides themselves, just contact Jim Kennedy, jimk@asresearch.com, and he can give you a copy of those. So that being said, let's move on because we have quite a bit of material to cover. So first things first, let's see what we're going to talk about today. Before we get into the leakage testing itself, I'm just going to cover some basics about why we perform safety testing, some potential shock hazards, and then we'll get into the actual leakage current. What is a leakage current test? Why are we doing it? And then after we cover that, I feel we can really talk about the leakage current test per the 3rd edition standard and what it talks about for requirements on a leakage current test. So there's some ground rules that we want to lay out for this, some basic rules for the leakage current testing and how you perform it, the measuring device that's used, and then, of course, the types of leakage current tests, because anybody who's ever dealt with the medical device standard and done this leakage current testing, you know there's a variety of them depending on your medical device, and then especially depending on the insulation barriers you do have in your medical device. You might have to do different leakage current tests to compensate for that and measure those. So the basic types are earth leakage, the touch current, also known as enclosure leakage, patient leakage, and then patient auxiliary leakage. And we're going to go into each one of those types, give a couple examples, and then I also have a couple video demonstrations using one of our leakage testers to show you one of the ways that this could be done. And then, of course, like I said, we'll show some of those videos. So why perform electrical safety testing? Well, really, there's more than 4, but the 4 main reasons are as follows: safety, quality, cost control, and liability. Obviously, for safety, you need to ensure that the product is not going to pose a shock hazard to the user. Obviously, whenever you're dealing with a standard, there is a slew of tests that are run on it. And here, we've just focused in on a narrow bit of that. And we've fallen under the spectrum of the electrical safety test and even gone even a little narrower and are talking about the leakage test itself. So this is just to make sure that the user is not going to run into a problem when they're using this device. Quality. Testing prevents faulty components from being installed in products by helping us catch workmanship defects. Obviously, if you put the product through its testing paces, you go through a testing lab, maybe you have a testing lab in-house, that goes a long way to making sure a product's safe. But that's the prototyping or the design phase. There's always possibilities that on the production floor something happens. Maybe a worker snips a piece of insulation. Maybe a piece of insulation gets caught in between 2 chassis points. These are all very possible scenarios that I have personally seen at sites. So it'll help you catch those defects on the way out the door. And then kind of falling in line with safety and quality, you have cost control. Following proper safety testing procedures can help identify production problems before the product is shipped, preventing a costly recall. And then liability is probably, of course, one of the big ones, because really the bottom line is the safety testing rests on the manufacturer. If you get audited and they find out you hadn't been doing your safety testing, it's going to be a big problem for you, because it's up to you, the manufacturer, to make sure that your product is properly tested before it goes out onto the market. So let's look at a couple potential shock hazards here. And this is some pretty basic electrical stuff. I'm sure a lot of you already know this, but I don't think it ever hurts to cover it. So here we're talking about contact made with one point of the circuit and then the user at a ground potential. And whenever you're grounded, remember, electricity always wants to escape to ground. You can think of ground as an infinite pool of electrons, so it's always trying to go back there. So if you make point or contact with a hot metallic, and what I mean by hot is that you have, let's just say, line voltage, or there's electrical current flowing through this metallic point. And you're at ground potential, and the current sees you as a low resistance path to ground or as the lower resistance path to ground, that's going to be a problem. So that is technically a shock hazard. But you don't always have to be at a ground potential for that to happen. You can come between two hot points of the circuit, and again, the thing to remember is that electricity is lazy. So if it sees those 2 points, let's just say in this example you see a guy going arm to arm, if those 2 points, if that creates a low resistance path, the current is going to go that way, unfortunately for us. So it's just something to keep in mind as we move through this material. This is exactly why we're running these tests. Because if you run a line leakage test, you would know with at-line voltage, if something happened with a fault condition, exactly how much current could flow through a person. Is that current level dangerous? Is it going to pose a hazard? These are the big questions that we're trying to answer in running these tests. So just doing some quick calculations here, and all I'm illustrating here is that depending on how you're contacting 2 points of a circuit, the human body has different resistance levels depending on what we're talking about here. So in that upper left-hand one, you can see arm-to-arm contact. And I'm giving it about 10,000 ohms of resistance right there, in which case we're talking about 240 milliamps of current. That is definitely enough to stop your heart. And that upper left-hand scenario, that's a pretty bad one, just per the fact that it's going across your chest cavity, and that's never a good thing. And actually, I think there's a typo there. That shouldn't say 10,000 ohms. That should be 1,000 ohms. Arm-to-arm contact, and this is assuming a very large contact area. As you can see in the diagram, the guy's got his palms open. So we're assuming contact area as if maybe you wrap each hand around something metallic about the size of a Coke can. So obviously we're assuming a very large contact area here, and we're assuming a worst case scenario. But if we're talking about a standard 240 volt circuit, and once again, that should say 1,000 ohms, not 10,000, that's 0.240 amps, which is enough to paralyze your heart muscle. It's actually more than enough. So in that middle one, we have a similar scenario, and again, that should say 1,100, not 11,000. Again, apologies, that's a typo on the image. But again, as you can see, 218 milliamps is more than enough to do some damage. And then the upper right-hand one, what I'm trying to illustrate there is how widely that the body resistance can change depending on your contact point. So now instead of a whole hand, we're just talking fingertip to fingertip. Your resistance of the body increases to about 20,000 ohms in this case, and that's a fairly conservative estimate. And as you can see, it goes down to about 12 milliamps. And that is a much more manageable current as far as being able to survive it. You're definitely going to feel a jolt at 240 volts at 12 milliamps, but the chances that that would be fatal, unless, of course, you might have a defib or something in your body that, or you have a medical problem, it's probably not going to be a fatal shock. So these are just things to keep in mind as we move forward with this material. So we're just talking about shock hazards, and that kind of leads us into the leakage current test. What is it, and what's going on with this test? What it is, it's basically a test used to determine the amount of leakage current flowing through insulation barriers on a medical device while the device is running. And that's a key point here. You want your device to be up and running. You want it to be in a state as if somebody was going to be using it. So like a doctor's going to be using this thing, or it's attached to a patient. You want the thing to be fully booted up and running. And we say leakage because we're talking about current that's flowing in the insulation itself. It's almost the same thing as a capacitor, really, because when current is flowing through a capacitor, we're talking about a dielectric material. Well, insulation is a dielectric material. We want to know exactly how much current is flowing through the insulation. because we use insulation in products to separate different conductive materials. Obviously, we're using the conductors to tell the electricity where we want it to go, and we're using the insulation as a barrier to protect us. Now, no matter what, there's always minuscule amounts of current flowing through insulation. We want to know how much that is, and that is the point of this test. So we're going to measure leakage current from earth or a chassis point or some other point back to a system neutral or line during what we call normal conditions, which I will abbreviate in this presentation as NC, and SFC, or single fault conditions. Now, these normal conditions are obviously, without anything going wrong, a normal condition, but we also have what are called single fault conditions, and these faults include a reversal of the polarity. So instead of line neutral, you're now flipping it in its neutral line. A open neutral, so you're basically opening a conductor in the circuit, and then an opening of ground. So opening or defeating your ground circuit to see what might happen. If there's a fault and you open your ground, what would a user be exposed to? And really what we're trying to do here is look at all combinations of these faults. And kind of the main point of a leakage test is we really want to see how much leakage is flowing through these barriers. So for a leakage test, we're going to power up the DUT with an operator selectable voltage source. I mean, obviously you're going to need some kind of source to power up your device under test, which I'm going to call a DUT here, so that you can get these readings. So we're going to make these connections and fault conditions through a series of relays, and technically if you're talking about 3 different fault conditions, a polarity reversal, an opening of the neutral, and an opening of the ground, you have 8 different possible combinations. One thing I want to point out here from the medical device standard standpoint is that a reversal of polarity is not considered a fault condition, but it is considered a test condition. So it is mentioned, it is not a fault condition, but you have to account for it anyways. And if you look at the diagrams, figures I believe 14 through 20 in the medical device standard, which we'll talk about in a little bit, it does show a reversal of polarity as a test condition, and it wants you to use that as a test condition to make these measurements. So basically what we're doing is we're measuring the fault current with this industry-specific MD, or called a measuring device, which simulates human body resistance. What I like to call the leakage current test is it's basically a worst-case scenario test. You're powering this thing up at a specific voltage, going through 8 different fault combinations, measuring what the human body would see, and seeing under these worst-case scenarios how much leakage current somebody's going to be exposed to. So if we're looking really quick at all 8 possible combinations, here's what we're dealing with. We have a relay on the neutral, we have a relay for reversal of the polarity, and we have a relay on the ground. So obviously we have 2 states with 3 different fault conditions. You have 8 total combinations. Now technically, for the medical device standard, you wouldn't need all 8, because the medical device standard does not say you need to do a double fault, which would be an open neutral, open ground at the same time. When I'm running the tests in the lab, I do all 8 anyways. It can't hurt to cover your bases, and if you do all 8 of these tests for every leakage test, you're pretty much covering your bases. You're going above and beyond what you need to do, which is never a bad thing. But you might see certain setups, certain labs, or customers test them with slightly less conditions, and that's okay, just as long as the main ones are covered. Now, let's take a quick look at what's going on here. And here is what we would see as a circuit for a line leakage test. So I'm just going to use my highlighter here. And you can see what we have here is this would be our input power over off onto the left. So this is line neutral coming in from some type of transformer. Could be an isolation transformer. That tends to be what I use, preferably a medical grade isolation transformer. And this comes in to power up the device. Now the device would be plugged in here. So just imagine you have something plugged in, you have power coming in from your variable source, and then you have various switches for fault conditions. So we have a neutral switch, our polarity reversal, and a ground switch. And that's what we're going to be looking at moving forward here. I'm getting a little feedback on the phone. If somebody could mute their phones, so we can make sure that we're not getting any noise. I'm hearing a little bit of noise here. Okay, so leakage testing per 60601 3rd edition ground rules. And what I mean by ground rules is these apply to all of the leakage tests no matter what type you're dealing with, whether it be earth, patient, enclosure. You test to the highest rated supply frequency. So for example, if your device operates 50 and 60 hertz, you're going to run the leakage test at 60 hertz. Again, like I said, it's worst case scenario testing. You're going to test normal conditions and single fault conditions. And again, keep in mind reverse polarity is not a single fault condition, but it is part of the testing, so you have to account for it. I believe in the diagrams for the standard, they call it switch S5, and it's going to tell you to do it in all combinations of S5. The equipment has to be fully energized and in a ready state, which means if you have a microprocessor-based device, let's just say an ultrasound, that takes a minute and a half to boot up, you're going to have to fully boot this thing up for that minute and a half before you start taking your leakage readings for these readings to be considered valid. And to throw another worst case scenario out there, we're going to test this at what we say is a highline condition. We're going to allow 110% rated mains input, i.e. if your medical device runs at 120 volt standard, we are going to run this test at 132 volts. That brings up an important point here, because for these types of tests, you're not going to be able to just use straight up wall power. That's not acceptable. Wall power is not going to give you this highline condition that you need. Not only that, but wall power can be quite variable. If you ever monitor wall power, you'll notice sometimes, especially depending on where you are, it might dip below 120. You could go as low as 110, and it's still coming out of the wall like that, or it could go a little above 120. You want a steady 110%, which is why I always recommend the use of an external power supply or a medical-grade isolation transformer, because you will get that steady power to do it. And then, of course, we need to measure it. Now, I already mentioned a measuring device. And with every type of leakage test across the industry, there's all types of leakage tests through various different standards. Obviously, we're focusing on the 60601 standard, so what we have here is the 60601 measuring device. It's a pretty simple device. I mean, we just have a 1 k ohm and a 10 k ohm resistor shunted by a 0.015 microfarad cap. The cap is in there to give us a frequency-weighted response, which really more stimulates the human body closely than just a straight resistance. With the human body, there's going to be some capacitance involved. So we want to know across a broad spectrum of frequencies, I believe all the way up to 1 megahertz, how much leakage current somebody's going to be exposed to. So your MD and your leakage testing device should be able to measure those leakage currents over a broad frequency spectrum. That's very important. Granted, you're only powering it up at 50, 60 hertz, but those other frequencies are on the line. They will exist, and that's going to affect your readings. So let's look at the types of leakage tests we're going to be dealing with here. These are the main ones, and I'm going per the standard on these. First and foremost is our earth leakage current test. This refers to Section 8745 in the medical device standard. Section 8.7 in general talks about the line leakage test, but we start hitting the actual descriptions for the leakage tests and figure references at Section 8745, and this is measured according to Figure 13. We have the touch current test, which I like to call the enclosure leakage, and that is Section 8746, measured according to Figure 14. Just so you guys know, I'm just briefly covering these here. We're going to talk about them more in depth as we move through the presentation. We also have the patient leakage current test, which essentially is measuring, let's just say, off a patient lead. Let's say you have an ECG electrode attached to a patient. Well, we would want to measure the leakage current on that electrode. Obviously, this electrode is going to have conductive contact with the patient, so we need to know exactly how much leakage current could come off of that patient lead while we're running these tests. This includes what we call a mains unapplied part leakage test. And that is a whole nother animal as far as testing goes, which I'll talk about in a few here. And then we have patient auxiliary current, which is basically patient lead to patient lead leakage current. As everybody knows, a lot of medical devices, I just mentioned a DCG, there's multiple patient leads. And there's insulation barriers between each of those patient leads. So if somebody has multiple patient leads attached to them, monitoring various functions of the body or whatever the case might be, we also need to know on top of just how much leakage current is going from one back to our system reference, we need to know between patient lead to patient lead how much leakage current is flowing between those points as well, because we may be dealing with a different insulation barrier. And if we have a different insulation barrier, we need to measure that leakage current. So what types of limits does the standard allow? Now, fortunately, in this case, the standard does outline very specific limits on exactly how much leakage current is allowed, which is nice because it takes the guesswork out of the equation. It tells us exactly how much we can have maximum, and if we exceed that value, it would be considered a failure. So for the earth leakage test, in normal conditions, your maximum allowable leakage current is 5 milliamps. For any single fault condition, it goes up to 10. Basically, they're accounting for the fact that, yes, when you have a fault condition, obviously you're going to have more leakage current because you have a fault in the system. However, it should not exceed that value. If it does, it's considered a failure. And there's another portion of the standard that points out that if you're not using the measuring device, and say you're just using something along the lines of a current sensing resistor for very specific cases, the maximum allowable value across the board is 10 milliamps. So that's pretty much your top of the bar leakage current limit for this standard when you're doing a leakage test. For touch current, it's a little different. Now the values are lowered because we're talking basically with touch current, we're talking about, let's just say, a chassis point on your medical device. Maybe you have a metallic part of the device that is not protectively earthed. They have to measure leakage current off there as well because there could be a fault, that chassis point could become energized, and somebody could touch it. So in that case, you can see the values are greatly lowered. We have 100 microamps for normal condition, and then for a single fault condition, that limit bumps up to 500 microamps. For the patient leakage, and when I say patient leakage here, I'm talking about general, which, remember, as I said before, would be patient lead back to system reference, and then auxiliary, which is patient lead to patient lead. There's a whole slew of values, and I would recommend that you reference tables 3 and 4 in section 873 to look at all these values, because it would be too much to cover them in the short time we have here. But those limits range all the way down to 10 microamps for something like a CF-type applied part on a patient lead, all the way up to 1,000 microamps for a normal condition on, let's say, a type B applied part. So there's a broad range there, and the standard clearly outlines for each type what you need so that you can set those limits in your leakage tester, or that your operator can keep track of those limits. So I'm obviously going to use the example of the devices we manufacture to show you how a leakage current test would be run. Now, as many of you know, there is a broad spectrum of leakage current devices on the market, but many of them operate in a very similar fashion. Like I mentioned before, we have these ground rules that we need to follow and very specific relays that need to be switched to measure leakage current properly. This is just one way of doing it. So you could use this example should you happen to have a different leakage current unit and not this particular device to show you what I'm talking about. So what we have here is we have power supply exhibited here, and we're bringing power into what we call our DUT input. This goes through the unit through a series of relays, and these are the relays that would simulate your fault conditions, and then that power is output on line, neutral, and ground to our DUT. So that's how we're able to boot up the DUT. We have internal relays which simulate these fault conditions, and then the measuring device is also in the unit so that we can get these measurements. You'll also notice two other connections here, and what these are probing points. Why would we need probing points? Well, if you have a patient lead, or for touch current, an enclosure point that you want to measure to, you're going to need probing points to do that. Obviously, you can't just measure that through the line, neutral, or ground connections. You need to probe out to that chassis point or to that patient lead, whatever the case might be, and you'll notice there's two probing points. Well, we might run into the case where we have two chassis points that we want to measure in between. In that case, you would need two probing points. Just like you'd need two patient leads, you'd need two probing points to measure leakage from patient lead to patient lead. It's all just a matter of how you set the relays internally. So basically what the earth leakage current is it's the amount of leakage current flowing through a product's insulation from the mains input line to ground. This one's important because basically what it is it gives you a measure of the total leakage on the product. It's telling you how much leakage is flowing back to ground from your mains between those 2 points, and that's a pretty important number to have. So here we have it set up for what we call a earth leakage test, and we can see here's our measuring device here, and we're placing our measuring device, as you can see here, between the ground and one of our mains conductors. Here I have it referenced to neutral, but obviously if you reverse the polarity, you would have it referenced to line. So we have the device plugged in here, and we're measuring between these 2 points. And as you can see, we still have our fault condition relays in here. But this puts the measuring device in the proper spot to be able to measure these values so that we can get a value for earth leakage current. So what's going on here? I'm just going to show you a quick example of exactly what's happening when we connect this. So let's break this down to a circuit diagram. Here we have the DUT plugged in, and you can see our measuring device labeled MD in the bottom right-hand side of the little box right there. And these are our fault conditions as well. So in normal conditions, you can see that our current is flowing from line to neutral right across S3, and it's pretty much bypassing the measuring device. So this is something to keep in mind when you're running a line leakage test. I actually get this call quite a bit, or I used to when I was doing more applications work, where people would call and they'd say, hey, I'm running a line leakage test with your unit, and I'm not really seeing any leakage current, and I know my device should have some. The first thing I ask is your ground fault, do you have a ground fault condition currently going on? Or in other words, is switch S3 or your ground switch open? Oh no, it's closed. Well, that's why you're not seeing leakage current. Because if your ground is properly functioning, you should not see much leakage current. You might see a little bit of stray or residual current, but it should be a very small value. If your ground is properly functioning, and remember, the measuring device is designed to simulate somebody touching the medical device. If my ground is properly operating and I go up and touch a medical device, that shouldn't be flowing through me. That current should be going back to the ground. So it's normal to see these really low or zero values when you have a closed ground condition for a leakage current test. Then, of course, we have what we would call our open neutral, in which case if you have an open neutral, your device under test is not going to turn on. You've essentially cut the circuit. So it's going to shut off and then boot back on when you close switch S1 or have a closed neutral condition. Then we have a polarity reversal, as you can see here. It flips going out to the DUT, and we want to measure leakage current in that case as well. And then finally, we have an open ground condition. Now you can see the leakage current flowing through the measuring device. This is really where we're going to start to see our readings. And if you are going to fail a leakage current test with an over leakage current limit, this is probably where it's going to happen, when you have your open ground condition, and that might be in tandem with a reverse polarity condition as well. And you might even have an open neutral condition at the same time. Like I said before, I like to cover all 8 scenarios. I don't see it fluctuate much when I do open ground and open neutral, but in certain cases you can see it rise just a little bit. So this gives you an idea of what's happening, and that's important for when we start some of these videos. Now, bear with me here for a second. I'm going to pull up a video of me setting up a line leakage test, and I'm going to need to share this. So I'm going to share my Windows Media Player, and might be a small lag, so I'm going to wait a second. So you guys should now see, I have the video paused, the main menu of the OMNIA 2 unit. And what I'm going to do in this video is you're going to see me set up a line leakage test. How would this be done? So obviously on this unit I'm going to say set up tests. And it looks like I already have one there, but I'm going to get rid of that and start from scratch to show you guys how I would do this. So I'm going to go ahead and add a line leakage test. And just so everybody knows, I'll pause this for a second. I am using a multifunctional unit here. Obviously we're not getting into the scope of the other tests. We're just focusing on line leakage. So what you can see on screen here is we have various limits that I can set here. And obviously you might not be using our leakage tester, but any leakage tester that you're using should have some sort of limit that you can either set or a hard set limit depending on the test that you're running. So to keep things simple, for the case of this demonstration, I'm just going to set my leakage high limit at 1,000 microamps, which is a pretty common high limit. I'm just hooked up to a dummy DUT anyways. I want to monitor my voltage to make sure it's set to a proper value. I have a 120 volt device, so I'm going to run 132. So I'll set my high to 135 to give me a little bit of playroom, and I'll set my low to 110 to make sure that I'm actually running the test. Say, for example, I didn't turn my power supply on, I'm not going to have any voltage. At least now it'll warn me, instead of it just reading zero leakage and me wondering what the heck's going on. I also have 2 timers here. I have a dwell timer and I have a delay timer. what the delay timer is that's going to allow me to boot. Let's say I have I mentioned before, a microprocessor-based device that might take, a couple minutes to boot up before I want to take a measurement. That's what your delay timer's for. It's waiting to make a judgment on pass-fail until it hits the dwell cycle. So like I mentioned here, I just have a dummy DUT, so I'm just going to keep my delay at 2 seconds and my dwell at 2 seconds. But would I have a device that, let's say, takes a few minutes to boot up? I'd probably put my delay at, let's just say, 180 seconds or 3 minutes, and then my dwell time at 2 seconds, because that's all I need to take my measurement. So now I need to set my measuring device. Since I'm doing medical, I will select the IEC 60601 UL2601MD. I'm going to select a ground to line condition, and ground to line, as we just saw in the previous example on that little chart, that is our earth leakage, because we can see that our measuring device is between our two mains conductors, ground neutral or ground line, depending on what you're running. So I'm not using any probing points at this point. I'm not doing a patient leakage test or a patient auxiliary. I'm just doing an earth leakage. So I'm keeping my ground to line condition. So next, I'm going to set continuous on. That's actually a feature unique to our units. Basically what that does is if you're running multiple leakage steps, it just keeps your device booted up, which is pretty handy if you have a 3-minute boot up time and I'm running 22-line leakage tests because I'm covering all conditions. You don't want your device to boot down every time because you're going to have to boot it all the way up again once it turns back on. So I keep continuous on to save myself some test time is basically what I'm doing here. This unit also has an internal power supply, so I don't have to worry about hooking up an external one. So I'm going to set my internal supply at 132 volts, 60 hertz. Now remember, that's my highline condition. I have a 120-volt device, so I want to set 110%, 132, at a 60 hertz frequency to make sure that that's running when my leakage test is. Now all I really need to do is set my various fault conditions. So my first test, I had normal conditions. Now I'm going to go through all my other combinations, and you'll notice here that when I did the opening of the neutral, you see it actually does it on the diagram. You can see the neutral switch is now open in a red state, telling you that I'm simulating this fault condition. So now that's the next test. Now I'm going to set up yet another test, and you'll notice that it's keeping all of my limits, which is good. That's going to save you a lot of setup time. So now I'm going to do a polarity reversal. You can see here I switch my polarity. Next, I'm going to set it up for an open neutral and a polarity reversal. And again, here I'm just covering all my 8 conditions. I'm just running through, making sure I'm covering my bases, that I have the proper test set up, opening my ground in this particular case, and I'm going to run just the entire series of tests. Now, one thing I want you to notice, because I will actually run these tests, is when I actually do run these tests, my first few, remember, I had my ground closed. So what you're going to see is for those first few tests, you're not going to get much of a reading. But once the ground opens is when you're going to see it kick in. So I saved my test file. Now I'm going to just skip down to my line leakage test. But before I do that, let me show you what I'm doing. Now I mentioned I just had a dummy DUT. So I showed you guys that diagram with the adapter box. Here's my dummy DUT. I just have a standard line cord, which I'm going to use to plug into the adapter box. So that connects my line neutral ground to my power supply. So you can see out of the back of the unit, I have line, neutral, and ground. So the power is coming out there. This case lead I actually don't need. That was for a high pot test, which is a whole different can of worms. So I'm not going to talk about high pot testing today. Anybody who's used our equipment knows we do high pot testing as well, but I don't need that return point for this particular test. We already have an internal measuring device measuring between ground and line for an earth leakage test, or ground and neutral, so we're just going to stick with that for the moment. So I'm going to go ahead and flip down to my line leakage test and push test. Now notice in the upper right-hand corner you can see the fault conditions. So there's an open neutral. And you can see I'm getting my 132 volts here from my internal power supply. Now there's the reverse polarity. And again, I'm getting pretty much no reading right now because my ground is closed, even with neutral and reverse. Now once my ground opens, now you can see I'm getting a reading. And now I've done a fault with ground and neutral, and you see the reading went up quite a bit in this particular case. And my test passed. So that's basically how you can set up a line leakage test. And once you get into it, it's really not that difficult. And many leakage testers out there, you would see a very similar scenario. So that was an earth leakage current example. Now when you're setting up your leakage tests, setting up a touch current patient auxiliary, the setup of the test is going to be nearly identical. You're going to set up all those same fault conditions. The only thing that's really going to change are where you're probing to and your leakage limits. So if we're measuring touch current, we want to measure the leakage current that's flowing through a product's insulation from particular points on the chassis back to your reference. So you need at least one measurement if you're doing this test. That could be from enclosure point to earth with, let's say, PE interrupted, even in the case that it's normally protectively earthed. If your enclosure points are not protectively earthed, you need to measure between earth and each point of the enclosure that is not protectively earthed. That's kind of the case I mentioned before. You know, if you have various chassis points that are not protectively earthed or not grounded, you got to measure from point to point as well as point to back to your reference to make sure that those insulation barriers don't have too much leakage current flowing through them. Now let's just say you have an enclosure that is all insulating material and does not have a bare metal chassis point. Well, in those cases, basically what they want you to do is simulate human hand contact, conductive human hand contact. So they tell you to take a 10 centimeter by 20 centimeter piece of conductive foil, copper foil, aluminum foil, anything along those lines works, and you place it on the enclosure, and then you can use your probing point, let's just say probe high in the case of the OMNIA, attach it to that foil so that you can get your measurement. Because what that's simulating is human hand contact, very conductive human hand contact with your chassis point for your touch current test. So in this particular case, and I'm going to use my highlighter here, you wouldn't have probe high to probe low. If I was just doing, let's say we have one patient lead, let's just pretend this relay is in this position. And let's say that we have a patient lead that we're connected to here. So I have my probe high connected to a patient lead here. So what we're doing in this particular case is we're still powering up the device. So our device is plugged in right here, and we're bringing in power here with our various fault conditions. We're powering it on, and now since we're powering on our product, it is a source of leakage current. And you're going to have some leakage current flowing back to this patient lead. So what's going to happen is leakage current is going to flow from your probing point through your measuring device back to your same reference point. So actually for this test, if we were just measuring one probing point, let's just say a chassis point or one patient lead, or we're doing individual patient lead testing, we'd actually select a probe high to line condition because we just want to measure probe high back to our line, our neutral reference, to get that value. We'd only use probe high, probe low if we were measuring, let's say, chassis point to chassis point or patient lead to patient lead, something along those lines. So just a slight difference in what we're talking about here. So again, we would have pretty much the same setup. We have our device powering up either through an external power supply, or if I'm using this OMNIA unit, it has an internal one. That's going to power up our DUT here. We're going to have our probe high on a patient lead or a chassis point. Leakage current is going to go from here through our probe high, through the measuring device, which will be here internally, and then back here to get our measurement. So general patient leakage current is just really literally patient lead back to your reference. And as far as a setup goes, like say you're using an OMNIA or another device that has a probing point, it's really no different than a touch current test. You're probing a patient lead instead of a chassis point, but your setup is the same. You might have a different high limit value, but as far as connecting to your device under test, it's pretty much the same thing. So it's similar to touch current in its measurement technique. Sometimes you also need to apply voltage from an isolation transformer, and they call it a separate isolation transformer. We'll just call it T2 in this case, or transformer 2, to your signal I/O while measuring leakage current. This is a little bit of a different case. Let's say you have a signal I/O port, an RS-232 port, or an Ethernet port on your device. What they want you to do is actually apply 132 volts from a separate isolation transformer to that signal I/O while you're measuring this leakage current, whether it be a touch current or a patient lead, to simulate basically a worst case scenario. because it is possible that if your medical device is within 6 feet of a wall outlet, that somehow a line voltage could contact, through fault or any other means, how it's plugged in, could contact that signal IO port. And if that worst case happens and somebody's on a patient lead, what's going to happen? Your insulation barrier from your signal IO port to your patient lead or your chassis point has to be sufficient so that you're not going to pose a shock hazard. So we're covering all types of scenarios. Now, I'm not going to get too in-depth on that one, and I know it's a tricky one, and I know if you have questions on it, you can always reach out and contact us because we have dealt with these types of tests before. And actually, in a few minutes here, I'm going to show you an example of such a test. So for patient leakage, we're going to have a very similar scenario. And once again, I'm going to pretend the relay's in this position. So if we're just connected, as I said before, to just an individual patient lead on our probe high, it's really not too different from the other test we just ran. We're still powering up our device, our DUT, through our input power. It's plugged in here. We have leakage current on the patient lead coming in here, being measured by the MD and going back to our reference point. And I still have my probe high to line condition because now I'm just talking about individual patient lead back to our reference point. And really it would be no different here. You have your probe high connected here to your patient lead, and that's circulating through here, through the measuring device internally, so that you can get a reading. Patient auxiliary is where the game changes a little bit, because that is measuring patient leakage current from patient lead to patient lead. So it tests leakage current through the insulation barrier between patient leads. Now you're going to need your other probing point. So now this setup is actually correct. You see I have probe high to probe low selected, and we have, let's just say, patient lead 1 connected to probe high and patient lead 2 connected to probe low. So what's happening is we power on our device, still plugged in, we power it on, and it is now a source of leakage current. So you're going to get some leakage current coming in through probe high, going through the measuring device, and measuring back to probe low. Think about this as pretty much, I mean, anybody out there who's used a standard voltmeter or LCR meter or current meter or something like that, you're just using 2 probing points. It's almost the same thing. You just picture it as 2 probing points, and you're just going between these 2 points and measuring leakage current. It would be no different than measuring voltage with a voltmeter between 2 points, except this time we're measuring leakage current. So in this case, my big giant, OMNIA unit is really acting as a giant probe. And you can actually use this technique to measure between any 2 probing points. It actually gives you a lot of flexibility because you can go between any 2 patient leads, between any 2 chassis points, and you can select it so that these relays automatically configure themselves to how you want it. So that's just an example here. So I saw a question come up on the side here, and I just thought I'd mention it because it is kind of an interesting question. Somebody asked, do you have a built-in isolation transformer in your power supply? The power supply that you guys saw me set up in that example, yes, that is an isolation transformer. You can use that for this type of testing. The one thing to keep in mind is just remember for the signal IO and for the mains on applied part tests, figures, I believe it's 16, 17, and 19 all show a separate isolation transformer, or they call it T2. You will need a separate isolation transformer to simulate those conditions. So just keep that in mind. I would be using my ISO transformer internal on the OMNIA to power up the device, but I'm going to need a different one if I'm doing those particular conditions. So the same thing here, except if I'm doing patient auxiliary, I have patient lead 1 and patient lead 2 connected to probe high and probe low respectively, and I'm measuring with the MD in between those 2 points. So I know I just covered a lot of information, so I have a couple more videos I want to show you guys, and then we're going to leave it open to some questions. So bear with me here for a second as I do an application share. Now this video you're going to see is going to be quite different because now what I've done is I've incorporated a scanning multiplexer into the mix. And this is to simulate the case where, let's just say I have multiple patient leads and I want to run this test in an automated fashion. Bear in mind, you don't have to run this test in an automated fashion. You could manually switch your probing points, but I want to do it fast, so I'm not going to do that. So bear with me here for a second. What we should see here is you'll see in the back, that thing on top, by the way, that's the scanning multiplexer. So what I have here is you'll see on the OMNIA, I've taken my two probing points, probe high and probe low. You can see them there. So those are my probing points for my patient leakage tests. And I've taken those up to a giant multiplexer. So we have probe high and probe low on channels 15 and 16 of this high voltage multiplexer. And then what I've done is you can see I've taken 8 patient leads, and keep in mind they're just simulated patient leads. I just have resistors on the other end of those. I have very high value resistors to simulate an insulation resistance. That's all it is. But now that I have these 8 patient leads on here, I can use this multiplexer to switch probe high or probe low to any one of those points. So not only could I set my probe high to line condition and do patient lead 1, 2, 3, 4 on down the line for my patient leakage test, I could also do patient auxiliary tests, switching probe high to probe low on any one of those leads. And I'll show you guys that here in a second. And like I said, all I have here are some big resistors. It's just a resistor network that I'm using to simulate this insulation barrier. So I'm going to stop sharing that, and I have one more video that shows me actually running this crazy little setup that I have right here. So let me pull up the video first and then share the application with you guys. Okay, so now you'll see I have the scanner on top, and I have a whole slew of leakage tests set up. So I'm going to go ahead and run these. And I want you guys to keep your eyes on the scanner, which is up top. So you'll see right now, if you look at the top right-hand side of the OMNIA screen, right under where it shows the fault conditions, where you see neutral, reverse, ground, you'll see my probe configuration is set ground to line, which means I'm running an earth leakage test right now. So the scanner's not in use because I'm just measuring from ground to line on the adapter box itself right there. So scanner, I don't need the scanner for patient points yet. But in a second, you're going to see it switch the probe configuration, switch probe high to probe low, simulating a patient lead to patient lead test. So right there, you can see, first of all, that my scanner channel lit up. Now remember, if you look on the bottom right-hand side of the scanner, you see that's channels, what we would say 15 and 16 on the very bottom right-hand side there. So 15 is lit up red, and right to the right of it, 16 is lit up green. So I've set channel 15 high, channel 16 low. Now over to the left-hand side of the scanner, you'll also see I've set channel 9 high. So now that I've set channel 9 high, I've essentially shorted it to probe high. It would be no different than me manually taking the probe high connection and connecting it to a patient lead. Then you'll see also that I have channel 1 set to probe low. That would be no different than me taking the probe low lead and connecting it to yet a different patient lead. So if we just say channel 9 is patient lead 1 and channel 1 is patient lead 2, I'm just taking probe high, probe low, connecting probe high to patient lead 1, probe low to patient lead 2, and taking a measurement. And I could do this for any number of patient leads I have connected here. So you see I have that patient lead 1 to patient lead 2 with probe high and probe low set, and I'm just multiplexing out these different measurements. Now obviously, I'm not getting a reading here because I'm just running it up an insulation barrier. I don't have voltage applied to these resistors. It's just a simulated setup. I could apply voltage to these resistors to get a value, but I really just wanted to show you how this would be set up. That's the more important point here, is to show you how a test like this would actually run. So I know that was quite a bit of information, and I covered quite a bit of material here today. Like I said, if you would like a copy of this presentation, please let Jim know. If you have questions after the webinar, you think of something, or you just want to talk about medical device testing in general in terms of line leakage, even if you want to talk about high pot and ground bound, which we also get involved in, email us, info@asresearch.com, and we'd be happy to answer those questions and go over your application. We've gone over quite a few medical applications, so we can certainly help you in that regard. That being said, I will leave it open if there was any questions that may not have been answered during the webinar, or if any pop up in the next couple minutes. Once again, I will say that our next webinar is on Wednesday, November 6th, and it's about solar panel testing. So if anybody's interested in that, I know quite a different industry, but if you know anyone that would be interested, please feel free to attend. This webinar will be available on our archives page in the next few days. We thank you very much for attending and hope to see you next time. We just got a question. Somebody asked about a video for mains on applied part testing. Now, obviously, you could see that I was doing some testing in my lab there. I do have a video that I put up on YouTube for mains on applied part testing. It's a lengthy video, so I didn't have it here. It's about 13 minutes long, but if you are interested in viewing this video, go ahead and shoot us an email, info@asresearch.com, and request that you'd like to see a video on mains on applied part testing, and that'll get directed to Syed and myself, and we can send you a link to that video. Somebody else asked if there was any kind of certificate for attendance to this webinar. No, technically there is not. This webinar is intended to be purely informative, so there isn't specifically anything along those lines. However, we have run into a situation in the past where a worker, for example, or a manager has shown this video to their higher-ups or other individuals at a testing lab and asked if this could be used for training purposes, and they have gotten positive responses in the past. So if you're looking for some type of certification or use this as training, please feel free to use this as a training video for in-house training and things along those lines, and feel free to reach out to your testing lab and see if you could use this as cert or partial cert for this type of testing.
Hi, Nick. We have a question from Ajay, and he wants you to expand on when you talked about switch S3, as you mentioned in the presentation. He's saying that the standard does not say to open the switch in case of earth leakage. So could you expand on that, please?
Yeah, technically the standard doesn't specifically talk about opening an S3 switch. Okay, so he is right from that standpoint. However, if you do look at something, for example, like figure 13 in the standard, you do have what's shown as a opening switch on something like a functional earth, or maybe a grounding point, or something that opens to the reference point. And in that case, you may want to open that switch to simulate that condition to be able to get that value of measurement. Now, like I said, everybody does the test a little differently, and you may run into a case where you don't want to open that switch, and that's fine. You don't technically need to. But the other thing to keep in mind here is if you don't open switch S3, you're really not going to get much of a reading because, again, your earth is in a functional position, and all your leakage current is going to go flow down through there. So if you want a proper reading, you're going to open that switch to get that value. So it looks like most of the questions have been handled. Again, if you want to see a copy of the video, please email us, let us know, and we can get that out to you. It's a little YouTube link, and I'll just do that on a inquiry basis, since I'm sure it's not everybody who wants that. But again, thank you very much for attending, and we will see you next time.
Hey, Nick, are you still there?